Welcome. This is the second experiment, and if you recall what we just covered in class, we did projectile motion. And you recall projectile motion is two-dimensional, and it's the arc that the projectile travels is a parabola. So we're going to be dealing with that today. So Lab 2 looks like this. You should have read it already. And we're going to talk a little bit. Now, if you recall, when we did Lab 1, we had to establish a control variable. Now, we're going to do the same thing in this experiment. I'm going to draw the picture of the experiment on the board here for a second. It's in the lab, but I want you to look at this. Here's the gun. And it's launching a ball. I'll put the ball right here. Okay. So it's launching a ball. Now, there's a height above the floor, okay, above the deck. If you were to drop the ball straight down, the bottom of the ball hits the floor. Okay. Now, we can call that anything we want. In the lab experiment, I think we called it Y0. Yeah, let's just call it Y0, because that's what it is. So that's how high Y0 is. So you got to measure that. Okay? Now, why do I need to know that to begin with? Well, I'm going to show you this from two approaches, and then you guys can take it from there. First of all, we know that Y equals 1/2 AT squared plus V0y times the time. Now, this ball has no downward velocity initially, so we can get rid of that term. So if I know the height, let's just arbitrarily, it's not quite, but I'm just going to put 100 in here for the sake of argument. If I know that this is 100 centimeters, which is how many meters? 1.0 meters. And I know that 1/2, the acceleration is gravity times squared. I can figure out the time that it takes for that ball to drop. Okay. Now that I know that, I'm going to call that time of flight. Like TOF. Let's make it like this. TOF. Time of flight. Okay. So if that's perfectly horizontal, when the projectile leaves, it's going to leave with an x0. And we know that I'm going to get rid of this for a second. We know that there's no acceleration in the x direction. So the time of flight will allow this thing to travel this far, x final, which in the experiment we called range. So if I take a piece of carbon paper and put it right there, and I know the distance out here where the ball hits, it's going to follow some sort of a trajectory like that. And since I know the time of flight, I can say range equals V0x times the time of flight. Now I can figure out what V0x is. V0x is your control variable. That's the muzzle velocity coming out of this launcher. So even if I take the launcher and turn it to an angle here, it still comes out with that initial velocity. In this case, we'll now just call it V0 because it's not horizontal. Here it's horizontal, so I can apply the X. But it's the same muzzle velocity no matter what the angle is. Okay? That is crucial. That's part one of the experiment. It's what you have to do, and you have to get this one right because you're going to use this V0 for every calculation the rest of the experiment. And that's all I'm going to say on it. So we'll stop right. Okay, now the first thing we're going to do is shoot this thing horizontally, and I'm going to show you this. This is the Pasco launcher. Now, one of the things I told you in your how to write an acceptable lab report handout was when you identify your equipment, you don't say the Pasco launcher because this is a Pasco launcher. It's a Pasco launcher. It's not the Pasco launcher. It's not the only one in the entire world. So you're going to say to somebody, equipment needed, a Pasco launcher. Okay, so now once we've identified we got one of these things, then you can refer to it as with a definite article. But initially it's any Pasco launcher. Now, couple things. It's got a plumb bob on the side here, so you can set the angle. Now I've got that set pretty close to 0, which is what I wanted for the first shot, horizontal. Now, you notice here's the lanyard for firing it. You need to figure out in the experiment who's going to be the cannoneer. Okay, but it's not cocked. Otherwise, you'd hear it snapping when I pull that lanyard. So now watch what I'm going to do. I'm going to push this thing in 1 click, 2 clicks. Okay. Now these are very consistent. The springs are good. They're consistent launchers. So once you establish V0 for 2 clicks, it's going to be V0 for 2 clicks always. And the hardest thing that you have to do is find someone that's got a little trigger touch. Instead of yanking this thing and shaking it and making it move, you just want to do it nice and gently. For the horizontal one, you can put the ball in the muzzle, 1 click, 2 clicks. Now it's ready to shoot. Okay. Now you're going to look out on the floor there. I think we can see it on the picture. No, we'll have to. Can we see it? No, not yet. There it is. Out on the floor is a piece of carbon paper. So now we are going to just fire this. Oh, we overshot. So we got to move the carbon paper out a little further. And that's not a big deal. And a lot of this is trial and error to get the ranging. And then what you want to do is I'm going to show you this now before we load up the second one. Is you're going to take a metric stick and you're going to measure from the muzzle straight down to the floor. And if you line this up right, it's the edge of the table. Okay. Now mine's not quite lined up to the edge of the table, but it's pretty close for this purposes of this demonstration. Then we're going to lay the metric sticks out here. Whoops. Well, that didn't work. Just unplug that. Yep. Yeah, that's good. Now, we're going to lay these metric sticks out. And when we actually do this experiment, we're going to tape this carbon paper down. So we lay these out. And I'm going to mark this one. Okay, somebody's going to hold this for me so it doesn't move. But I'm going to mark this. I'm going to put a mark right here. I'm going to say that's my 160 centimeter line. So now when the thing lands, if it lands right here, all I have to do is measure from 160 out. I know how far it went. Okay, so let's just try one and we'll see. And after that, it's up to you guys. So, got to do the, got to load it, prime the cannon. Okay. 1 click, 2 clicks. Okay, stand by. Let's move this one just so more professional. Ready? Here we go. Stand by, fire. Oh, I hit the stick. Of all the things to do, I hit the stick. Okay, well, we get to shoot again then. Wow. I bet I can't do that twice in a row, but I probably will. So let's move it over. 1 click, 2 clicks. Let's shoot this. Let's see how repeatable this is. If it hits a stick a second time, you'll know it's dead on repeatable. Ready? Shoot. Boom. Ah, I hit the stick again. Not bad. So, not that that's what I was trying to do, but I want to demonstrate to you, just move it a ½ inch or so, that these Pasco launchers are fairly repeatable. So now we'll do it one more time. Okay. And now we'll shoot. Here we go. Good. We got a shot. Okay. Good shot. Now, let me just show you what this sheet will look like when we get done with it. Okay, I marked the 100. Oh, it hit twice there. Look at that. There's 2 shots that are dead on repeatable. Okay, that's is about, because remember, we're measuring from here. This was 160. This was 160. You can see I've marked it right there. Now all I got to do is take a ruler, measure out to there. But look at the longitude, the distance is almost dead on. So these are pretty accurate little machines. And that's all we're going to do on that one, and we'll stop it right. Okay, welcome back. Now, I want to show you something before we get into the next part of this experiment. Okay. If you'll notice, the muzzle is right here. And when you do the calculation for the range equation, the muzzle shoots to the same exact height. So that range equation is only valid from height to height. On the other hand, we measure everything from the table. So we're going to have to figure out how to compensate for this height from the bottom of the muzzle to the table. You're going to have to measure that. Now I have this set for just about 30 degrees. I think it was 30. And so we also need to know what this range is, because we're going to end up saying that if this is this high, then the launch point relative to the table is back over here. So you have a tangent function. Tangent of 30 degrees relates the y and the x, okay? So you just have to recall that when you shoot for every angle, you're going to need a y. I think we called it y prime in the experiment, okay? So if you look at this page, you'll see how it's laid out, and you have to account for that, okay? Remember, if you have a question, always ask yourself, what is my reference? And the reference in this case is the tabletop. So you have to account for the tabletop from the muzzle height where it's launched. So when we determine the height, for example, calculated, it's going to shoot from here to some height up the meter stick, okay? But it really, from the table, is this much has to be added to it to do that calculation, okay? Now, I don't know how clear I just was explaining this, but I want to make sure that you understand everything is referenced to the table. So the launch point in the x direction is back here. So you have to take this measurement and add that x distance to it. And the height measurement is referenced to the table. So you have to calculate from here up and add that distance to it. Okay, that's about the best I can summarize that. And if there's any questions, I'll stop here for a second. Okay, now we're into the meat of the experiment. Here's what we've got. The Pasco launcher, and it's set, this one right now is set for about 45 degrees, give or take. We've got the hoop with the ring, the center of the ring, and it's on the stand. And then we've got some carbon paper where it lands. Now, I want to point out the measurement differences. When we measure this is real data. This isn't theoretical. This is the real data. So the real data says the ball left here and it traveled over to here. But if we did a parabola, we would say it left back at the base of this gun, which is that X distance from the muzzle, and it went all the way from the X distance out to some point here. So that's the range from the muzzle to the range to the muzzle, which would be over here, plus this distance. So when you go in and you read the lab report, the equation says compensate the range by X on the launch end and X on the landing end to X. For the height, however, the height equation, we went from the table up to the ring. And you measured that. You measured it directly because we know where the ring is. We know the height. We'll measure it to the arm of the height, the arm of the ring, and then we shoot. Now the equation says you go from the launch point up. So you're going to calculate that H, but you're going to have to add this Y to it, okay? So note what you do for corrections. We say add 2x to the range, okay? And that gives you the mathematical correction for 2x to the range. The launch starts here and lands out here, so we'll add the x to it plus this range, okay? Remember, you're calculating everything based upon the table being the 0 point. The table is the 0 point. For the height, we're going to shoot it up. We can measure that height, but then we calculate it, and we've got to compensate the calculation by this height on the launcher, okay? So we'll demonstrate one, and then we'll feed you the data. Okay, if you will, sir. Okay, 2 cocks, because we already know the launch velocity. That was a control variable. 1, 2. Okay, stand by to shoot. Right through, I think.
Right through.
Okay, good shot. And we'll show you that it's repeatable. Do it one more time if you would, please, Alvin.
All right.
1, 2. Okay. Right through. That was dead through. Okay. So now we could go back and measure the height to here, down to the table, and we know the launch, the real data. That corresponds to the calculated data, which is calculated from here to here, plus this height, okay? We know the launch range from the muzzle down to where it hit the paper. To make that equal to all the calculations, we add the x to it on this end. The calculated range is from here to here, some height that's equal to it, and it's got to be compensated by an x and another x, okay? And that's all I've got to say on this experiment. We'll go through the data.